Hi everyone, last day for this week. We're gonna go over a topic once again from Math 103, which was briefly introduced to you, and so the first video or so is gonna be revisiting those definitions and properties. So I already wrote this out in case you read it because it's not new. So I'm just gonna go with it. The whole story for complex numbers begins with a definition, and it begins when we try to solve an equation of this form: x squared plus 1 equals 0. There is no real solution for this because when you square any number, it's always positive, meaning it's always more than 0. And then if you add 1 to it, it's never going to give you 0. And you can check that. This is a plot of y equals x squared. So the plot for y equals x squared plus 1 would be this graph raised by 1. And this never goes through the x-axis, so it can never have a solution. One way to circumvent this problem is to define. We define this number I, called iota, to be a solution of this equation. This means we define I to be a number such that I squared plus 1 is 0, or I squared is negative 1, or equivalently I is the square root of negative 1. And it turns out that just by making this one definition, we can find square roots of all negative numbers. Why? Because, for example, square root of negative 16 can be written as square root of 16 times square root of negative 1, which becomes 4i. And you can verify that if you square this, this is 16i squared, and I squared is nothing but negative 1, so it's negative 16. Similarly, for any a greater than 0, I can write the square root of negative a as root a times root negative 1, which is root ai. This number is called an imaginary number as opposed to a real number. At this point, we can define a complex number now. Complex number is any number which is written in the form of a plus bi, where a and b are real numbers. A is called the real part and b is called the imaginary part. For example, 7 plus 2i. You cannot combine them to make it 9i because 7 is a different number from 2i. In fact, it's a different type of number. 7 is real and 2i is imaginary. And we say this complex number has a real part 7 and an imaginary part 2. You can also have things like 4 minus root 2. Then it's a complex number which has real part 4 and imaginary part negative 2. Then in Math 103, you learn some operations on complex numbers. Let's start with a simple one, addition. Basically what this here is saying is that when you add complex numbers, you add the real parts together and you add the complex parts together. So in this example, z1 plus z2 is going to be the real parts and the complex parts added. So that's going to be 5 plus I. Same story with subtraction. I subtract 7 minus negative 2 plus I negative 2 minus 3, making sure I distribute the negative to get 7 plus 2, which is 9, plus I negative 5, or 9 minus 5i. So in a way, you can think of it as addition or subtraction of polynomials, right? So the x terms, combined with x squared with x squared. Similarly, the I terms combined with the I terms, and the non-I terms combined with the non-I terms. The next operation in increasing order of complexity is multiplication. When you multiply, all we are going to do is FOIL out. So when you FOIL out, there's going to be 4 terms. But I squared is negative 1. So you're going to end up with 2 of these terms which have an I in them and 2 terms which are real. Okay, so you end up with number plus I times another number, which is a complex number. So here, for example, this is going to be 7 minus 2i, negative 2 plus 3i, negative 14 plus 21i plus 4i minus 6i squared. That's negative 14. Negative 6 times negative 1 is positive 6. 21i plus 4i is 25i. So negative 8 plus 25i. Next operation is, you can say, kind of unique to complex numbers, but you have seen this in rational functions in 103. Radical rational functions. The conjugate of a complex number, z is the variable we use for complex numbers, is denoted by z with a bar on top. And what it is you just flip the sign of the imaginary part. So if z is a plus ib, then z bar or conjugate of z is a minus ib. For example, if it's 2 plus 3i, the conjugate is 2 minus 3i. If it's negative 2 minus 3i, the negative 2 part remains the same. You only flip the sign for the imaginary. Since it's already negative, flipping it means making it positive. The last operation is division. That's why the reason we talked about conjugate is because we use conjugates here. So when you divide, we multiply and divide by conjugate of the denominator. So this should remind you of the rationalizing denominator. So it's sort of like similar process. Now I left this as a blank for you to fill in. Why is this a2 squared plus b2 squared? Well, if you look here, that's a difference of squares, which means it's going to be a2 squared minus ib2 squared, which is a2 squared minus I squared b2 squared, but I squared is negative 1 and negative times negative becomes a positive. In fact, that is the reason why the division works, or why we use conjugate, is because we know that when I multiply a complex number with the conjugate, I'm going to get a real number, which is just going to be a2 squared plus b2 squared. So it kind of works out here. Okay, quickly looking at example. So 2 plus 3i, 3 minus 4i, conjugate is 3 plus 4i over 3 plus 4i. So all I have to do on the top is distribute, and on the bottom I'm going to have 3 squared plus 4 squared, distributing. 2 times 3 is 6 plus 8i plus 9i plus 12i squared. That is 6 minus 12 plus 17i over 9 plus 16, negative 6 plus 17i over 25, negative 6 over 25 plus 17 over 25i, which is a complex number. Okay, so it always works out. And this is a complex number because it's of the form a plus bi. A, the real part, is negative 6 over 25, and b, the complex imaginary part, is 17 over 25. So that is sort of the extent to which you've learned about complex numbers in Math 103. Try and make up some more problems and practice some multiplication, division, and stuff. I'm going to end this video here, and then we're going to continue talking about graphing complex numbers, and then eventually using some trigonometry and polar coordinates to explore complex numbers a little bit.